Okay, how does that look?
There you
That's
go.
normal. Yep.
Okay, there. 50-50 chance and 100% probability of getting it wrong. So this month I thought I'd just talk about some very basic stuff about antennas. We have some new people here and they might find this of a little bit of interest there. And there might be a couple of tidbits here for some of the more experienced people. But we're going to talk about antennas, just some basic stuff about antennas, not a bunch of detail stuff. I can take each one of these probably bullets and spend another whole uh, training session on each one. So we're going to touch a little bit about coax, a little bit about polarization, and then we're going to talk a little bit about dipole, ground plane, and talk about beams, or also known as Yagis. So just as an overview, there's three parts to an antenna system. You have to think about your antennas as a system out there. It's just not appropriate just to look at one individual piece of that system. But for that antenna system, you have a coax, and that's the wire or the cable that ends up getting the RF energy between moving it between your transceiver and your antenna. You have your antenna itself that's somewhere up in the air, and then you have a support system that kind of keeps that antenna up in the air so it can operate. Now not going to talk about the support system this time here because that's a whole nother time that I can spend a lot of time and discuss on. So let's get out of the way some of the technical part, nitty gritties there. Well, let's talk about definitions. So let's talk a little bit about radiation. There's lots of to know about radiation. There's horizontal radiation, there's vertical radiation. There's also what's known as isotropic radiation. So whenever you see that word isotropic or you see a small I, it'll normally mean isotropic. So that's radiation. An antenna in that radiates equally well in all directions. So that means that antenna will radiate in a full 360-degree azimuth pattern when you see isotropic. Another term that we're going to be talking a little bit about that you need to have some idea what it means, and that's dB, decibel. And in ham radio, it always refers to our RF power. And that number is expressed, or the math that gets performed on that is always in a logarithmic, yeah, I'm not saying things very well, logarithmic measurement. And it's measured as gain. So it's either gain or loss. So it's always comparing how much power you have from one point to another point. Something that's really important is gain, and that's the increase or decrease in amplitude of a signal, and that again is measured in dB. And again, that's always expressed in a logarithmic scale. And later on, when you'll understand why it's a logarithmic scale and what that logarithmic scale really means, but it's not just one, two, three. It's actually it's a scale that goes up very, very quickly. So whenever you see a thing called dBi, and I mentioned it earlier, that I means we're talking about isotropic radiation. So that's gain measured relation to an isotropic radiator. So this isotropic radiator, when you get into looking at gain for antennas, it's kind of this magical or mythical, it's really mythical, uh, point of reference um, that we make all of our references to for measuring how well an antenna is doing. So let's hit on coax a little bit. Feed line. That's the cable that connects between your air transceiver and your antenna. So that's the guy that moves the RF signal back and forth between your antenna and your transceiver. So my best advice here is don't use cheap, lousy coax. when you really cheap out and you lose and you use really cheap coax, you're throwing away a lot of valuable signal, and it just doesn't pay. You need to throw a few extra dollars at it and get some good quality coax so you don't end up with a bunch of losses.
I got a question for you, Mike.
Sure.
So how you're looking, you're at the local electronics store looking at these big reels of spools of coax. How can you tell if you're looking at good quality or not, other than the price tag?
Yep. Well, okay, for right now, I have a whole program I do on just coax. So
Hmm.
I can bore you to ad nauseum. So do you see the coax to here over on the right hand side here? So
No,
this is
is there, all
that's
I see are your individual video pictures. Is there something else you're presenting?
in the slide there. There should be a roll of coax that's embedded in the slide on the right side of it. You're not seeing it?
No.
Is anybody else seeing it?
I see the slide normal.
I can see it normal too.
Okay. So George, something's not right as far as what you're seeing there. And
Hmm.
Anthony, do you have any suggestions there?
You might look at the top right. There's usually a button that says view. You might change the view
Swap
stuff.
shared screen with video?
Uh, oh, it should be like
No.
like standard side by side.
No, no, I don't have it. I've got a small flag icon that says swap shared screen with video.
Oh,
No.
I think try that.
Ah, okay. Now I see the slide and I don't see the rest of you guys.
Ah,
Yep.
okay. You're not missing out on anything there.
All right,
But
continue.
you at least you see that big old that honk and roll of big fat coax. Generally speaking, not always, but generally speaking, the fatter, the bigger the coax is around, like that's half inch around, the better the quality is. Um, if you want information, actually, let me finish, get to the bottom of this slide here, and we'll go back to what you're talking about there. So, one key thing to remember when you're looking at coax, and there's a bullet here that you always want to check the specs. You always want to look at the specs of that coax. And when you look at the coax, you look at what the coax number is, the RG number on it, or LMR, or whatever reference it is, and then there'll be some number on it, and then it'll be a grid, and that grid basically gets broke out by frequency. As the frequency goes up with coax, so does the loss happen. So as a rule, you try and keep your coax losses, and also the longer the coax is, the more losses it is. So that grid is always expressed in 100 feet increments. So if you only need 50 feet worth of coax, you cut the loss by 50%. If you need 200 feet of coax, you multiply the length of coax or the loss there by 2, and that tells you how much you're going to end up losing. But you always want to go back to the specs on that coax, because that tells you how much loss you're going to have. The other key part of that is as the frequency goes up, so does the losses. So through the HF band, the losses aren't too awfully bad at that on what you end up losing. But as you get into that 2 meter band, and when you get into that 70 centimeter band, that 440 meter band, that loss gets quite significant. And so you really have to start thinking about quality coax when you get up into those higher frequencies. So let's see that. Yeah, the fourth bullet down there. Always check the specs for the dB loss per 100 feet of your coax. And as the frequency goes up, so does the losses. And when you get into the VHF, UHF band, those losses get quite substantially. So in those bands there, you really got to step up to the better coax there. So the other point there is hams always use coax that's 50 ohms, 50 ohms impedance, period. That's what the hams use. A lot of times in some of these charts or when you're out there shopping, you'll see RG6 or you'll see other types of coax that's 75 ohms, and that's stuff that we don't use here in the ham radio community. So let's talk a little, get into antennas now. So I got some couple, about 3 different antennas there on the bottom of that slide. George, you can see that?
Yep.
Okay. We're on the same page. So when we're putting up our antennas, we want to make sure that they're oriented correctly for the kinds of use that we're going to have. Because as those antennas transmit and also as they receive, they're going to be looking for a magnetic field coming in at it that has a certain polarization. Those 2 antennas on the left, that's all vertical antenna. The diagram on there, that shows vertical polarization. That shows how it's coming in on that antenna. The antenna over on the right-hand side is oriented in a horizontal direction. So there it's going to perform best when everything that it's talking to has horizontal polarization. So as a generality, is that for VHF, UHF, you normally end up using vertical polarization for FM communications. If you're in a VHF, UHF, and if you're using single sideband, there typically those people are going to be working for distance and you're going to be using horizontal polarization. It doesn't mean that you can't communicate, but you're going to end up, if you don't have things in the right polarization, the right direction, either up or down or horizontally, you're going to have some losses. You're going to be losing out on what each person is going to be communicating. That signal is going to be somewhat truncated. So let's get into the vertical and horizontal stuff a little bit more. So verticals are generally used for HF and UHF antennas. Horizontal is generally used for HF and also for single sideband when you're in VHF, UHF. Vertical polarizations provide better ground waves, so that means that RF is going to do a better job of tracking the nap of the ground. Horizontal polarization means that most of these guys are going to be high frequency operators. That's going to be using the ionosphere. The ionosphere is the magic that we get in HF operations where we get long distances because that does a nice job of coupling and dealing with the ground plane effect and getting up into the sky and traveling long distances, that horizontal polarization. So here's a key thing to remember. If, especially like in VHF, UHF, if you have one person transmitting with a horizontal polarization, another one in vertical polarization, you can see upwards to a 20 dB signal loss. So if you take that, 20 dB and chop it up into, divide it by 3, you can see that that's going to be a huge amount of signal loss, huge amount of signal loss. Now, it doesn't always happen that way. So I have a final bullet down there. There are exceptions to all of the rules above. So all the rules that I put out there, that's what the most likely experience you're going to have with polarization. There are still exceptions to that, and that's for a whole nother discussion. Be getting into all the exceptions. I don't want to confuse anybody at this point in time, but those 5 top bullets there are pretty much you can use those things verbatim. So let's talk about a really simple dipole. in HF operation, the simplest dipole, the simplest antenna you can have is a dipole. Basically, you have coax that comes up into the middle for your feed line, and you got two wires out the sides of it. One connects to the shield, one connects to the center conductor of the coax. Oh, I should have put up a slide to show what the inside of a coax looks like. And you tie a rope on each end of that and hoist it up into the tree or put it up on some poles or whatever you want to do to get it up into the air. But that is a simple, basic antenna. And I'll tell you what, it just works. There's nothing simpler. There's lots of stuff that's better than a dipole, but if you want something that you can depend on real easily, use a dipole. The one thing to be concerned about is that a dipole is only resonant on one band. So if you put up a dipole for 20 meters, that antenna is only going to work on the 20 meters there. There are some exceptions onto that, but generally you have to add in a tuner and things start getting a little complicated on that. And there are other variations, many, many different variations on a dipole that gives you different kinds of good benefits and also causes you some other problems. But again, this is guy only gets really used in HF operations. The gain on this is usually about 2.15 dB. So it has a very, very modest amount of gain, but it does have some. It is directional. So broadside off of that wire is the radiation pattern that it will have. And I didn't include, there's all kinds of graphs and stuff I can bring up and show you all kinds of show you exactly how that thing radiates. But just remember on a simple dipole, that radiation pattern is broadside to that piece of wire that's up in the air. Okay, let's talk about beams. And there's another term that you'll also hear out there called a Yagi. And back in the old days when the guy that originally developed the concept of using beam up there, he was actually a Japanese guy. He presented a paper on it. His last name was Yagi, and that just basically stuck in the industry for everybody calls the thing a Yagi up there. So what it is a long pole. The center part is your a beam across there, and you have different elements on there. You'll have one element that's usually a driven element, and then you have a reflector and a driver on it. Excuse me, reflector, and I can't remember the right names for some of this stuff. But anyway, the one on the left there is for HF, and that's a good old standard 3-element beam that kind of a bread and butter, very easy to find, lots of those things out there. The one over on the right side is for VHF. They also have UHF models. They also have combo models that will run both VHF and UHF on it. But each one of those elements, usually the longer that beam is, the more elements you have, the higher the gain you can get out of it. So these guys are more expensive. These guys on the HF, you will virtually only see those things horizontally polarized, which is the way it is. On the VHF on the right side, that is also horizontally polarized, but that antenna you'll see both vertically polarized or horizontally polarized. It depends on what the ham operator wants to do as far as operating. If he wants to work a bunch of sideband and try and get more distance, you'll see that thing in a horizontal configuration like it is. If you just want rag chewing, get into repeaters and talk on locally, then that thing will be in a vertical orientation. So the neat thing about these guys, the antenna on the right, that is only good for one band, 2 meters. You can get other variations that can do 2 bands. The antenna on the left, that guy there will do 3 different bands. So you can get multiple bands out of it. There's also ones that'll do 4, 5, and 6 different bands out there. But the expense on that goes up quite significantly as you get more complicated with that. So the beams are very, very directional. And generally that pattern that it looks out there, depending on the beam, is somewhere between 15 to 30 degrees as far as the pattern that it will look out in front of the beam. Now, the nice thing about when you get into beams, you can get stuff that will get all the way, easily 6 to 15 dB. 6, that's twice the. So if you have a 50-watt transmitter, that means that when you are talking with a 6 dB worth of gain, that 50 watts is going to turn into 100 watts. So you can get quite a different significant improvement on performance. Now, some of these VHF, UHF beams get quite long, really, really long and really big, where you can get all the way up into the 20 and 30 dB worth of gain. So you can start off with 100 watts, and pretty soon you're up almost to a kilowatt as far as effective radiated power with an antenna like that. But again, those are pretty expensive. So let's go to the very basic one, good old ground plane. This is the easiest one to put up. You can get some of them that'll do both VHF, UHF. That's pretty common and easy to do. These guys here, you can get ones that can have gain anywhere from 3 dB to all the way up to 12 dB. So when you get into a 12 dB ground plane like that, these get to be pretty darn good size, and they start getting pretty darn expensive. They're vertically polarized. You can see that mast, or the driven element there, is pointing vertically. It radiates in 360 degrees, so you don't have to worry about turning it, twisting it. Just stick it up there and you'll receive whatever comes in at it all the way around in a big wide circle. They're relatively easy to install, and generally speaking, they're fairly modest to price-wise. And that's when you're a new ham, that's where you're probably going to start off with, is something that is just a ground plane up there that will get you on the air, get you 360-degree coverage, not a whole lot of expense that you have to worry about, and it'll get you on your VHF bands real nicely. So let's talk about magic. So the magic of antenna gain. So I kept throwing out this number of gain, this thing about gain. And that's the magic of antennas. When you throw more money at these antennas, you can get more gain, and you get a huge improvement as far as transmitting and receiving. So, and another thing is, remember that this gain is reciprocal. That means that if it's going to double the transmit power going out, it's going to also double the receive power coming in. Very cool. That's a very important point right there. So a dipole, again, usually like around 2.5 dB, and that's normally used in HF operations. Mid-price ground plane, for that does both VHF, UHF, probably sub $100. That's going to probably get you right around 7 to 7.5 dB worth of gain. Nice boost there when you throw a little bit of money at it. Like that one that I had up there, I think that was like about a $56 antenna.
I have a question for you.
Sure.
Is there any relationship between gain and SWR?
No. Nope.
Okay.
Only that you have to deal with SWR in the context of feed line and antennas.
Right.
So generally generally speaking, like if you're just talking about a VHF, UHF antenna, like this guy right here, this guy is already pre-tuned for you. If you put in a chunk of coax, that's some pretty decent coax that has factory connectors on it, you're not going to have to work with SWR. You're not going to just don't really have to worry about it. If you try putting on your own connectors or crafting your own antenna, then you need to start probably thinking about SWR. If you go out and go to one of the swap meets and you find someone has a whole bunch of used um, coax underneath his table that he's selling for cheap, there you might have some problems with the SWR. You don't know where it really came from. But I would venture to say 9 out of 10 times or even better, if you buy a antenna off of Amazon or any of the other ham sites, ham radio outlet, and buy some coax from them that already has connectors on it, 9 out of 10 times you're not going to have a problem with it. Just put it up and go. And then I talked about 3-element antennas. Usually you're going to get for HF, those are big, bulky, quite large critters. You have to have a rotator, you have to have a tower, you have to have something, a bunch of stuff to support it. It gets pretty expensive to get that thing up in the air and also just to buy it. And that'll get you 8 dB. Now I have an absolute monster that's up on top of my tower that I can get almost 16 dB worth of gain on it on HF, and that works all the warp bands and also 20, 15, and 10. Also gets 17 meters and also 12 meters out of it. So that's 5 bands, but that's a very expensive antenna, and it's not appropriate for beginners. So let's wrap this guy up. HF antennas.
Mike, can I maybe make a buzzkill comment for a minute?
Go for it.
That gain is not magic necessarily. That gain is on an antenna is kind of like a balloon. So you don't get gain in one direction without losing it in another. And what a lot of these, especially vertical antennas, do is you lose gain going up where you don't want it in order to get gain going down. So it's kind of like squeezing a balloon. You can squeeze the balloon to make the gain go in one direction, but by squeezing it, you make the gain go down in another direction. So it's kind of a zero-sum game where you have a round, an isotropic is a perfectly round sphere, and you're compressing that sphere in certain places in order to get the gain to go out into others.
Yep. Yeah. One of the things that's missing here is that I deliberately did not include any of the plots to show how all that works.
Yeah.
So that's for another discussion when we start digging in deeper into how an antenna works and how it gets that kind of gain.
Awesome. Well, sorry if I stepped in with advanced topics, but yeah, thank you.
Don't worry, it's always appreciated, but occasionally there is a method to my madness here. So
I thought there was a madness to your method, but if you want to go the other way around.
I get it confused sometimes. So VHF, UHF antennas, normally you operate those on FM, and you always keep them vertically polarized when you do that. And the exception is if you want to do sideband and do some of the more weird stuff out there on VHF, UHF, then you'd probably have an antenna that was horizontally polarized. So always use quality coax. I'll just underline that a couple more times. Pay a little extra money to get good quality coax, and that'll last for you and give you good performance and not lose a bunch of signal for you. So antenna gain dB is I still contend that's your magic power multiplier when you take a look at that dB. But you also, like Anna was talking about, when we get into this a little more detail, you see how it gets created, and you'll see how you can gain and lose that type of gain, that type of gain. But always consider when you look for antennas with good gain factors, it's a good value for the dollars. So beams, Yagis provide the most gain. So you're really not going to find any other type of antenna, category of antenna that provides you the most gain. It always comes back to that beam out there. So anyway, that's it, folks. And let's see if I can get the page back here and see if there's any questions or anything that anybody might have.
To reiterate a little bit of something that Mike said, antenna gain is almost always cheaper than amp gain. Amp gain is really, really expensive, and amp gain doesn't work on receive either. So you would much rather have gain out of your antenna system than you would putting a $6,000 2 kilowatt amplifier in it. This is coming from somebody that has a big amplifier and not a great antenna.
Go, Scott.
Okay, Mike, I got a couple of points I want to kind of maybe either correct or clarify. Let me work backwards. First of all, Yagi, the name Yagi antenna is not from some guy who published some sort of paper. It was in a way, but Yagi, actually, the antenna is known as the Yagi Uda antenna, and Uda is really actually the one who is really responsible. He was Yagi was a professor at Tohoku University, and he had an assistant by the name of Uda. Let me see. It was
Okay.
yeah, Hidetsugo Yagi and Shintaro Uda. Uda was the assistant. He is the one who actually invented the this antenna, and they published the first paper on it in 1926 in Japan. And since then, Yagi kind of co-opted the whole thing as he was the professor. And, you know, in the Japanese system and also in the old European system, the head professor was the boss. So they did whatever they wanted. And he actually stole the idea from Uda. And even though Uda was his assistant and they published, you know, on this antenna together, Yagi ended up making all the money on it because he sold the patent rights to, you know, United States, to Britain, to Germany, and elsewhere. The Yagi antenna was used for radar purposes during World War II by the Allies and the Axis. And it was developed, you know, a lot of the science behind the Yagi was developed at that time. So that's where the name is. So it's actually the Yagi Uda antenna. Yeah, that's the way it is. And it was developed in Japan in the 1920s. And the other thing, going a little bit further back in your talk, on the RG6, yeah, it's a 75 ohm cable. I use it and a lot of other hams use it. Right now I have it for my VHF work because I have a long antenna run, or sorry, long cable run to my antenna for 2 meters. And RG6 has the lowest loss. You know, it's very cheap cable, but it's very good cable because it's used. The reason why it's cheap is only because they make tons of it for cable TV. And that's really where it's used commercially. But if you can, it's sold in all, you know, like at Home Depot and other stores. You can probably even get it from Xfinity for free, you know, a whole roll of it because they just throw it away. You know, they just use it like it was coming out of you know, the tap. In any case, it's very good cable for high frequency stuff. So for
Now,
at
do
least
do you end up transmitting on that cable?
oh yeah. Yeah, it works quite well. It will handle quite a bit of power at, you know, moderate powers, and I do it all the time. And it works great. It has the lowest loss. The only other 50 ohm cable you could buy that would be close would be RG213 and maybe LMR 400. And that's more expensive, and you can do that. I just happen to use the RG6 because I had tons of it, and it works great. You have to put F connectors on it. It's got a foil. It's got a double shield with a foil, aluminum foil, and regular braided cable. But you have to use an F connector. Well, you don't have to. It's the best way to do it. And then you can buy PL259s that have an F connector adapter on them. and that's what I do, and it works great. And I've had it up like that for years. You know, you could use it for HF, and I've done that, but you probably would prefer to use 50 ohm cable there. But 75 ohm, it doesn't matter if it's 75 ohms or 50, as far as your SWR is going to be.
So you're saying that you still are able to manage a reasonable SWR on that?
Oh yeah, it's you know, I mean, if the antenna impedance is matched properly, then the maximum you'll get is 1.5 to 1 SWR because it's just 75 ohms to 50 ohm system, you know. So it works. I mean, I have never had a problem with it, and it's a cheap way to go if you don't want to spend the money for the more expensive stuff. I mean, the recommendation would be, yeah, go buy the more expensive coax, but I have over 100 feet of run, so that's why I went the RG6 route.
Hmm.
And it works okay, you know, it works fine. So I just wanted to just throw that out
Okay.
there.
It works okay and is also commonly used in RX antennas. So
Yep.
my RX loop is RG6 and 75 ohm cable. The impedance mismatch doesn't matter all that much on the RX side of things.
No, not at all. You won't even notice it. Not that small of an impedance mismatch anyway. So anyway, yeah. So I just wanted to point that out too. So RG6 isn't bad. When I bought my 500-foot roll of it, it was like 30. I think the full 500-foot roll cost $35 over at Home Depot.
Wow.
Yeah, it was really, now it's much more expensive than that, but you know, you can still get it cheap. But I would only recommend it in a case like I have with long run kind of situation. Because if you look at I'm looking at a chart here, like the loss chart for different coax types, and say 100 meg, or even let's go 200 megahertz, kind of in between, you know, 2 meters and 70 centimeters. So at RG213, 200 megahertz, you get 3.3 dB of loss per 100 feet. RG6 is 2.8 dB of loss per 100 feet. RG8 is for 5.4 dB, and RG58, don't touch that stuff, that is 7.3 dB. Loss at, you know, that's almost 10%, like 80% loss per 100 feet. So, you know, and then the better stuff, they have cable that is made for like really high frequencies, microwaves. And then, I'm sure that's very expensive, like RG9914, RG9913, and other types of microwave type cable. And of course, the next thing would be hardline, which is very expensive. So, or go to window line or something like that.
It is. I got my hardline for free.
Where'd you get it?
I'm not going to tell you, Scott.
Oh, okay. I'm sorry. I'm slow on the uptake there.
I know.
Sorry.
Coincidentally, there was that commercial radio station that had those off the air for about a week while they were waiting for new feed line.
Are you saying I stole Feedline, Anthony? Is that what you're going here? I am not a thief, for the record.
Well,
Okay.
somebody
Yeah.
stole a 200-foot tower that was used by an AM broadcast station in, I think it was Mississippi, Alabama, right? They stole the whole tower, 200 feet of it, an AM radio station. Nobody saw it overnight. They took the whole tower down and hauled it away, and nobody was the wiser. They took them, I think, 3 or 4 months to figure out who stole it.
I worked, for the record, I worked for a place where we hosted a Hughes satellite downlink station, and they were decommissioning it. There were 2 big 10-foot dishes in our parking lot that they were taking out, and they were pulling out all this 3/8 and half-inch hardline. I'm like, well, what are you going to do with that stuff? They're like, oh, we're going to throw it in the dumpster. And I told them the back of my car looked a whole lot like a dumpster, and they believed me. So all of it went into the back of my car, and
Very
now
good.
I have a bunch of 1/2 and 3/8 inch
Very
hard.
good.
I think I mentioned it here before, but an interesting thing about 3/8 inch hardline, if you can get a hold of it for HF purposes, is that the connectors, the PL259s for RG8, will fit directly on 3/8 inch coax, and you can solder it on. So you don't have to buy all the expensive specialty connectors for the 3/8 inch coax. You can just solder it up on there like you would an RG8. It's actually easier to solder because you don't have to worry about the braided shield melting into the dielectric so much or anything like that. You can gently heat the solid copper. So if you're interested, and at HF frequencies, 3/8 inch coaxes or a hardline is the bee's knees.
Yeah. The bigger it is, the better.
Any other
Hmm.
questions before I hand it back to net control here? Back to Anthony.
Oh, or pontificating from Scott and myself. I mean, I think I'm done pontificating. How about you, Scott?
Yeah, I'm done for the night.
Can I ask a
All right,
question real
we'll give
quick?
Mike a break.
Yeah.
Mike, you talked about horizontal polarization for single sideband at VHF and UHF. What would make single sideband different than FM?
The single sideband, typically on 2 meters, there are several nets that get together, and these are guys that talk between, let's say, um, Medford and Seattle,
Hmm.
and there you have the ability, if the ionosphere or the things are well enough set up where that horizontal polarization allows them to get that kind of distance.
Okay,
You
thank you.
said- Oh, 2 meters?
2 meters, yes.
Wow.
Wow.
Yeah.
Yeah, there's
Yeah.
every week on Monday, actually tonight. Is it Monday or Tuesday? I have to look on my schedule. But anyway, Monday or Tuesday night on 2 meters, there's a group of guys that get together where they talk from here over to Central Oregon, up to Seattle, down to Medford, Roseburg. Um, it's uh, um, it's pretty good as far as some, and it all depends on the conditions. They can't do it every week, but that's what they use for all their horizontal. I've tried I tried using vertical and I couldn't even get in their ballpark. But flip it over to horizontal and yeah, I could hear those guys.
Oh, I wanted to say
Thank you.
one more pontification, Mike. Yeah, as far as that is concerned, that's really true for line of sight situations. But a lot of times we get into repeaters. I've used horizontal. Like I have speaking of Yagis, I have a 2 meter Yagi from Corvallis, say to Silverton or above Silverton. There's a couple of repeaters up there, and particularly the WA7ABU repeater. So I've flipped my experimentally. I've gone vertical and I've gone horizontal polarization, and because it's not line of sight, I'm bouncing the signal all over the place. There's some flipping of the polarity, and at least a good chunk of the signal gets polarized the correct way if I'm horizontal. But if I'm vertical, we don't really know what happens to this, the polarization of the signal sometimes. And that's true for, especially line of sight types of communications like VHF, UHF. If you go to HF and you're using the ionosphere to bounce your signal, then the ionosphere is going to circular or elliptically polarize your signal anyway, or your radio waves. So there's it has no meaning, vertical or horizontal polarization for HF if you're really using the ionosphere there. So
Yeah.
yeah.
That's some of the magic in this craft.
Yeah. But for strictly line of sight, yeah, if you cross, you have, a vertical and the other person's holding their handheld horizontally. Sure, that's true. They'll get a 220 dB, attenuation of the signal probably at the one or the other HT, but that's, I think, a very specific situation. So usually, and for most repeater work, most of us don't have line of sight to the repeater. And so, if we did, most of us are vertically polarized anyway. So that's, I don't know how many people have tried it horizontally, but I have, and without line of sight, and it seems to not matter too much.
Okay, Anthony,